Hello everyone. Today I'm going to talk about our compiler Shiftry, which we have developed at Microsoft Research India. Shiftry enables running recurrent neural networks or RNNs on tiny IoT devices with small memories. This work has been done in collaboration with Vivek, Seshadri and Rahul Sharma. We are living today in a world of IoT. Smart devices have found their way into a wide array of applications like smart homes, transportation, smart cities and smart healthcare. How do these smart devices work? IoT devices collect data from the surroundings. They then transmit the collected data to the cloud, where it undergoes processing like ML inference. The cloud then returns the inference results to the device, which can take appropriate actions. However, there are a few problems with this approach. Transmitting data affects latency of the system and takes a lot of energy, which can drain the batteries fast. In addition, transferring data from the source to the cloud makes the data vulnerable to data breaches. To avoid these issues, one can consider eliminating the need to transfer data to the cloud by running ML inference algorithms directly on the IoT device itself. Typically, IoT devices have two types of memories. A read-only flash memory, which can hold the model parameters of an ML algorithm which do not change throughout the program run, and a read-write memory, which we call the RAM, which can hold mutable program state variables. However, the amount of memory which is present on these devices is very low. On an Arduino Uno, a device commonly used by makers working in the IoT space, the flash memory is 32 kilobytes, whereas the RAM is only 2 kilobytes. In addition, these devices typically do not have any floating point units. This presents a challenge to running ML algorithms directly on IoT devices. These algorithms are very hungry for resources. Deep neural networks require several megabytes or even gigabytes of memories, orders of magnitudes more than what these devices can provide. In addition, ML algorithms use floating point operations intensively, which are not natively supported by these devices. Recent work has produced novel ML algorithms which work very well on real-world applications while using only thousands of parameters. These models include variants of decision trees, nearest neighbors, and recurrent neural networks. Note that IoT devices typically work with time series data, and RNNs are the model of choice for this domain. These algorithms are targeted to be run on tiny IoT devices. However, even though the number of model parameters is small, there are several practical challenges when it comes to running them on tiny devices. As we have seen before, IoT devices have no floating point units and very low flash and RAM memory. The first challenge is the lack of floating point units, due to which such operations have to be performed in software, which drastically worsens the latency of the code. This problem has already been addressed by the C. compiler, which converts input code that uses floating point operations into code which uses only integer operations. C. aims to reduce latency on hardware without floating point units, while ensuring the accuracy of the integer code remains good enough. However, C. maximizes accuracy assuming that the target device will always have sufficient memory to run the code, which does not hold for our RNN benchmarks. The second challenge is the low memory resources on the device. Even though we have algorithms which are targeted for IoT devices, these algorithms are not written with the exact device flash or RAM constraints in mind. Even if a model may use only thousands of parameters instead of millions or billions, it may fail to fit on a particular device for some dataset. Memory constraints are hard because a model which exceeds either the flash or the RAM limit even by a few bytes will fail to run on the device. One may manually tune the code to manage the memory consumption, but this process is tedious and error prone. Present-day compilers for embedded devices fail due to not managing the memory consumption adequately. We take a compilation-based approach to tackle the problem. We provide an input DSL which can concisely represent a wide variety of ML inference algorithms. Given device constraints, the input program is compiled into C code which can directly be run on the given device. The main contribution of Shiftry is to handle the constraints introduced by the memory limits of the device. We now discuss how Shiftry tackles the practical challenges of running ML algorithms on IoT devices as we discussed previously. To tackle the lack of floating point units, Shiftry converts the floating point input code into integer-only code, similar to C. We use standard fixed point arithmetic, which I will demonstrate with a simple example. Suppose we have this floating point number 3.1416. This number can be represented using the 16-bit integer 25736 along with a scale 13. We can convert this representation back into floating point by dividing the integer by 2 raised to the scale, in this case 25736 divided by 2 raised to 13, which is just 10 to the power minus 6 of the actual floating point number. We can also represent this floating point number using the 16-bit integer 1608 along with a scale of 9. Converting this back into floating point, we get 3.1406, which has a higher error, 10 to the minus 3. Suppose we use 8-bit integers. 3.1416 can be represented by the integer 101 with a scale of 5. The deviation from the actual floating point in this case is much higher, 10 to the minus 2. Yet another representation is 25 with a scale of 3, which has twice the error. We can see that it is preferable to use a higher scale and a higher bit width for a more accurate representation of the underlying floating point number. We first discuss how do we assign scales. We run the floating point code on the provided dataset and profile each variable to compute the maxima and minima. Suppose for one such variable var, the range is minus 3.1 to 2.7. We want to assign the highest possible scale for better precision. However, our assigned scale should ensure that the corresponding integers for both extrema, minus 3.1 and 2.7, do not overflow. In this case, if we use a 16-bit integer, a scale of 13 is optimal, whereas if we use an 8-bit integer, a scale of 5 is optimal. Note that assigning a scale requires the bit width of the integer to be known. So we assign all variables a bit width of 16. Note that converting from a 32-bit floating point code to 16-bit integer code reduces the model size and hence the flash usage. However, this reduction in flash is not sufficient for some models. If we use 16 bits for all variables, many of our RNN benchmarks fail to run on the UNO as the generated code is too large to fit on the flash. On the other hand, if we use 8 bits for all variables, the generated code easily fits on the flash. But in this case, the accuracy of the output code on our RNN benchmarks is terrible. In some cases, the accuracy is equivalent to that of a random classifier. Due to this, we use different bit widths for different variables in the program. Unfortunately, there's an exponential number of possible bit width assignments, but Shiftry takes an exploratory approach where it generates and evaluates multiple integer codes to obtain a good bit width assignment in linear time. We demonstrate Shiftry's approach through an example. Consider a program with 4 variables a, b, c and d. If we generate an integer code with all variables using 16 bits, we get an accuracy of 97%, but the code does not fit on flash. What happens when we assign variable a 8 bits and the rest 16 bits? We get a code with accuracy 96%, but it still does not fit on flash. Trying the same with other variables, denoting b gives accuracy 92%, c gives accuracy 67% and d gives 94%. None of these programs fit on the flash, so we need to try out demoting multiple variables to 8 bits. We order the variables by decreasing accuracy when one of them is demoted to 8 bits. In this example, that order is A, D, B and C. We then cumulatively demote variables in this order. First we demote only A, then we demote both A and D, and so on, and evaluate all of these codes. Shiftry attempts to demote as many variables as possible while ensuring the accuracy is acceptable and the model fits within the flash budget. This helps to improve the latency of the resultant code, as 16-bit operations are much more costly than 8-bit operations. In this example, Shiftry outputs the code in which A, D, B use 8 bits. This algorithm compresses the model size enough to fit within the flash memory constraints on all of our benchmarks. We now discuss how to manage RAM. Existing memory allocation techniques used by present-day compilers do not work on our benchmarks. Consider the code snippet shown on the left and the memory allocation diagram shown on the right. The axis represents RAM usage and the red line is the RAM limit of the target device. If any variable crosses the red line, the code will exceed the available RAM and not run on the device. Note here that the variable A is only used in the first 2 instructions, B is used in the second and third instructions, and so on. In ML inference codes, variables have a very limited range of instructions where they are live and need memory. But existing compilers like Arduino IDE or C. keep memory reserved for all of them until the function exits. Variables occupy memory even after they are inactive, leading to unnecessary memory bloat, as is shown on the diagram. Let us consider dynamic memory allocation, where we allocate a variable just before it is first used and deallocate it after its last usage. The maroon line is just above the next instruction to be executed. We only label instructions which perform computations. Before instruction 1, A is allocated, and before instruction 2, B is allocated. After instruction 2, A dies and is deallocated, creating a small empty space. C cannot fit into the empty space, so it's allocated after B. After instruction 3, B dies, creating a large empty space. But the variable D is so large it cannot fit in this space. It has to be allocated after C, and hence the RAM usage crosses the device limit due to fragmentation at the beginning of the memory, even though the total memory available is larger than D's size. However, it is possible to fit these variables within the given RAM limit. Let us take a step back and go to the program state after instruction 2. If we had known a large variable was incoming after instruction 3, we would have assigned C in a way such that just before instruction 4, D would have fitted in the empty space at the start of the program, as we can see here. The issue with using dynamic allocation was that the memory was getting fragmented as variables were allocated using a very simple heuristic by the device, which aims to lower runtime overhead. It should be noted that for ML inference algorithms, the sizes of intermediate program variables and their live ranges are known at compile time. This enables us to eliminate the memory allocation overhead from the runtime itself. Shiftry simulates dynamic memory allocation at compile time. This means that Shiftry statically computes the exact memory location of a variable and uses that to generate the output code. Since we delegate the memory allocation to the compiler, Shiftry is able to use computationally intensive and robust algorithms to minimize fragmentation. In case fragmentation still occurs, Shiftry injects a defragmentation call to the output code to reduce RAM usage. So how does Shiftry perform compared to existing tools? We compare it to CDOT, which is the state-of-the-art in compiling ML algorithms to tiny devices. The following results were obtained on the Arduino Uno board on the benchmarks used by CDOT. First, accuracy drop. Here, accuracy drop is defined as the accuracy of the floating point code minus the accuracy of whatever code we are examining. Accuracy code of the floating point code is naturally 0. We note that Shiftry generated code has an accuracy almost 1% better than CDOT generated code. Second, relative latency. This is the latency of the code being examined divided by the latency of the floating point code. Here again, we see that Shiftry generated code is almost 40% faster than CDOT generated code. We see the same trend with relative model size. Shiftry generated code is 25% smaller than CDOT generated code. Shiftry outperforms CDOT in terms of accuracy, latency, as well as generated code size on the models that CDOT is able to fit on the Uno. However, unfortunately, CDOT is not able to fit RNN benchmarks on the Uno. We take an RNN model called FastGRNN for our experiments. This model is targeted for IoT devices. In this graph, we will compare Shiftry generated code against code which uses 8 bits for all variables and code which uses 16 bits for all variables. Here we know two things. For a code to fit on the Uno, it must fit within 32 kilobytes of flash. Any code taking more than that will not be able to run on the device. Second, the accuracy of the target code should not be very low compared to the floating point code, else the code will lose its value. So we have a small green region as shown on the graph where a code can be deemed as acceptable. If we consider homogeneous 16-bit codes, even though they have very good accuracy, they do not fit within the flash constraints of the Uno for some of our benchmarks. Similarly, if we consider homogeneous 8-bit codes, they comfortably fit within the flash constraints but suffer terrible accuracy loss. However, Shiftry generated code is able to get the best of both worlds for all of our benchmarks. Shiftry code has an accuracy similar to that of the 16-bit code as well as having a model size comparable to the 8-bit code. Given that so far the results presented are all on the Arduino Uno, one may wonder that whether Shiftry loses relevance as better hardware come up. A thing to note here is that as hardware improves, ML models also keep getting bigger. So the problem of compressing ML algorithms to fit within the constraints of a hardware is here to stay. To demonstrate the generality of Shiftry, we use it on a bigger RNN-based model called RNN Pool. This model is an order of magnitude larger than our FastGRNN benchmarks. It has over 150,000 parameters. We target an ARM Cortex M4 class device for this algorithm, which has 256 kilobytes of RAM and 512 kilobytes of flash. Shiftry is able to compress the RAM usage of the floating point code by 32 times, and the flash usage is compressed by more than 3 times and is able to fit the RNN Pool inference code into the device successfully. I would like to conclude by saying that there is a trend to run ML inference algorithms on tiny, resource-constrained IoT devices. To that end, we provide Shiftry, a tool which, given an ML inference algorithm and device constraints, is able to generate code to run directly on the device. Shiftry improves upon the state of the art for existing benchmarks and is the first one to run RNNs on an Arduino Uno. The source of Shiftry is available online, and I invite everyone to try it out. Thank you.